Okay, so the title of this section is Area and Distance. And so far we've talked a good bit about area, but not at all about distance. So, if I have t representing time, and I have v of t representing velocity. Let's just say time was in seconds and velocity was in meters per second. Okay. I know in general that the absolute value of velocity is equal to the speed with which an object is moving. Velocity, remember, is a signed quantity, so the sign indicates what direction we're going in. Okay. But if v of t is bigger than or equal to 0, so if our velocity is non-negative, just like we've been requiring our height function, f of x, to be non-negative in this section, if that's the case, then velocity is the same as speed. Now, in general, that's not true. Velocity is signed and speed is not. But if we're talking about something that's just moving in the positive direction, so its velocity is positive, then I can use velocity and speed interchangeably. Now, I'm going to just refer to this as speed, because in the next section we're going to start allowing velocity to be negative as well. And then what we get when we calculate an area using velocity as sort of our height function is a little bit different. The book does just talk about velocity, but they make it clear that velocity in this section is positive. Now, let's just suppose I had time here and v of t here, and I did have that my velocity was constant. Let's just suppose it was, 20 meters per second. And let's suppose that it was constant at that rate for 4 seconds. Okay. Well, if I take a look at this area that I have between the velocity function, which is determining the height of this shape, over this time interval, let's take a look at what that area is. That's 4 by 20, but if I look at the units, that's 4 seconds by 20 meters per second. If I were to multiply that, I would get 80 meters. Okay. So the area here, I can sort of think of as a metaphor for the distance. This is actually giving me the distance that I have. And anytime I have a formula where I multiply two things to get another, I can sort of represent that as an area where I just put one quantity as the base and the other quantity as the height. Okay. So the area of this rectangle I'm thinking of as representing a distance just by assigning units of time to the base and units of meters per second to the height. Now, if I have something like so, I'm actually going to just draw in the first quadrant because I'm going to have time be non-negative and velocity be non-negative. If I have a changing velocity over some time interval, but that velocity is non-negative, so it's really my speed, this area, the distance, or the area between my graph of speed and the time axis, this is also going to represent the distance that's traveled by an object. Okay. So, let's suppose that we have a particle that's moving. And let's suppose, I am going to go ahead and use v of t just because that's going to be consistent with what the book is doing. But I'm just going to make a note that this is actually the speed, not just the velocity. Let's suppose that v of t is sine of t plus 1. And let's suppose that's in meters per second. And we're working over the interval from 0 to pi. Okay. And what I want to do is estimate the distance And this time, rather than choosing left endpoints or right endpoints, I'm going to create an upper sum. I'm going to rig it so that I know I'm getting an overestimate. And the way I'm going to do that is on each subinterval, let xi star, my sample point, be the x value where v of t is greatest on that subinterval. Obviously, I could create a lower sum as well. If I were doing that, I would simply let xi star be the location at which I had the lowest speed instead. Okay. So let's use a regular partition and 4 rectangles. Okay, so that's what I want to do. I think I'm going to need a picture because I'm going to need to know what this looks like in order to be able to pick out the location where it's going to have its biggest value on each subinterval. So I know what sine of t looks like on this interval. Sine of t would just look like this. Now I'm moving that up 1. So that's just going to be a vertical translation up 1. So instead of the starting and ending points being at a height of 0, they're now at a height of 1. Okay. So we've got something like so. I'm trying to find the area between this curve and the t-axis. So I'm going to just draw in a wall here, and the y-axis here serves as a wall as well. So I'm looking for this total area here. Okay. All right. If I look at the interval from 0 to pi, and I'm chopping it up into 4 pieces, we said, that means the length of each piece is just going to be pi over 4. So my delta x is pi over 4. I start at 0, here's pi over 4. 2 pi over 4 is pi over 2. Then 3 pi over 4. And then 4 pi over 4 is pi. So I can mark off those points here. And what I'm going to do now is I'm going to create a table of values, but I'm going to just list xi star and the speed at, sorry, these are t values, not x values, ti star and the speed at those representative times, because they're not necessarily left or right endpoints. Okay. So I've got here's pi over 4, pi over 2, 3 pi over 4, and pi. Now on this first subinterval here, I can see my function was increasing, so the biggest value here does occur at that right endpoint. So that's going to be pi over 4 as my representative time. And I would just extend across that time interval so that I've created this rectangle right here. Now the next subinterval goes from pi over 4 to pi over 2. I can see that once again my function is increasing on that interval. I probably should have indicated at pi over 2 we're at the high point there. That's when sine is equal to 1. So I'm going to take that as my representative height and extend across like so. So here I was choosing pi over 2. Let's fill in those heights. Sine of pi over 4 is root 2 over 2, and then plus 1, because that's my formula for the speed. Sine of pi over 2 is 1, plus 1 would give me 2. Okay. Now my next subinterval is from pi over 2 to 3 pi over 4. Now on that interval, sine starts to decrease. So the highest point occurs at that left endpoint of pi over 2. So I'm actually going to choose pi over 2 as my representative x value here as well. Pi over 2 is the t value, the one t value that's shared between that second and that third time interval. So we extend across and get that. That would also have a height, or speed, of 2. And then from 3 pi over 4 to pi, I can see my function is still decreasing. So the highest point is at the left end point there. I'll extend that height across the interval. That means I have to just extend this vertical line to finish that rectangle. And we've got this. So that was picking 3 pi over 4, where the sine is root 2 over 2. So the speed is root 2 over 2 plus 1. So that's my upper sum. I rigged it so that for sure we would get an upper estimate. Let's see what that estimate is. So I can say my distance is approximately, and it's basically a rectangle plus another rectangle plus another rectangle plus another rectangle, okay, where each of these rectangles is sort of symbolic. This is representing a time, this is representing a speed. Speed times time will give me distance. Okay, so this one was root 2 over 2 plus 1 times the length of time was pi over 4, plus this one, the speed was 2 times pi over 4. This one, the speed, which we're representing as the height of this rectangle, was also 2 times pi over 4. And this last one, the speed, was root 2 over 2 plus 1, all times pi over 4. Once again, because we used a regular partition, that base, which in this case is the time interval, is the same, so I can factor it out. So that's pi over 4 times root 2 over 2 plus 1 plus 2 plus 2 plus root 2 over 2 plus 1. These two are going to combine to give me 2 copies of root 2 over 2, or just root 2. So I've got pi over 4 times root 2 plus 1 plus 2 plus 2 plus 1 is going to be 6. I'm just going to distribute that, so that's going to give me root 2 times pi over 4 plus 6 pi over 4, which would reduce to 3 pi over 2. So that would be my estimate for the distance. And in this case, because speed was in meters per second and time was in seconds, I should make sure I include those units, that would be meters. So we would estimate that over these pi seconds, my particle traveled root 2 pi over 4 plus 3 pi over 2 meters. But I know it actually traveled a little bit less than that because I set it up so that this was an upper sum, so I knew it would be an overestimate.